Is just a small fragment of history that's highly important in statistical physics, but it's a really interesting historical episode, and one that I think you'll find has resonances with a lot of stuff that you care about in broad philosophical issues. In fact, as the other presenters have been going through their material, I've been noticing, oh, I'm going to talk about that, no, I'm going to talk about that. So you'll see a lot of familiar things coming back. I take it you all know I put all this stuff up on a website. So you should have all gotten an email from, I think Wayne, you sent out the email. It's got, so this PowerPoint's available there. You can download the thing and do whatever you want with it.
From Rob Reed.
I'm sorry?
From Rob Reed.
Robbery?
Rob Reed sent the email.
Oh, Rob Reed, okay, all right. There are also links to papers. I've put some links up to some of my own papers. But more importantly, because I'm going to be talking a lot about Einstein, I've put up copies of the original Einstein papers. So there are 4 Einstein papers from 1905 that I'll be talking about. Sorry, there are 3 Einstein papers from 1905 that I'll be talking about, and I've got them up in both German and English if you want to see them. So all the sources are there, and I expect that everyone's probably read and studied everything, so there's probably no need for me to say anything more. Any questions? No. All right, okay, all right. I know the chances that you've all gone and looked at this stuff. So, okay. All right, so I thought I'd start out with something useful, and that is a way of making money. Now this is one of those. Now I know that you're not of the type that would go to bars, drinking establishments, and indulge in risky gambling behaviour. But were you in such a mind, this is a surefire way of making a little bit of cash. Right? I know some of you will know the answer to this, so you should keep quiet. But others of you won't. This is the question. In 1905. Einstein published a bunch of works of some significance. Special relativity equals mc squared and a whole bunch of other stuff. For one of those, he was awarded a PhD. And so, of course, the question is, which was it? Which was that? Right? Now, if you don't know, there's no way you can ever pick it, because it's the one work of 1905 that is almost never talked about. In fact, you can completely overlook that it's there if you just follow the, if you just follow the more superficial histories. Okay, so that's the warm up, and you'll find out if you don't know what it is in a few seconds, which that particular work was. So, for a warm up, I want to give you a bit of a sketch of what Einstein's papers of 1905 look like. I've put them all up here. I don't know how readable that is from back here. That's probably about the smallest type I'll have. Oh, okay, that's pretty readable. That's great. It was a very good year for Einstein. The Annus Mirabilis, the year of miracles. It surely deserves the name. Almost everyone knows about these 2 papers here. They're put up in order of publication, although that's not really quite the logical order, but that's the order we have. Everyone, of course, knows about the special theory of relativity, which was published which was received in June. A separate, very short paper gives you E equals mc squared. And then there are 3 papers that I will be concerned with. These are the papers that deal essentially with matters in statistical physics that will interest us. There is, of course, the light quantum paper, the photoelectric effect paper, which appeared first chronologically in a Nolan deficit. Then there's this is the paper in which Einstein proposes the light quantum. Then there's the Brownian motion paper. This is the paper in which Einstein uses a prediction of the phenomenon of Brownian motion as a way of estimating the sizes of atoms and making clear that you will have to take them seriously. And then there's the doctoral dissertation, right, which is a new determination of molecular dimensions. And what Einstein does there is the following. He looks at the known physical properties of dilute sugar solutions, and by looking at the viscosity and diffusion properties of dilute sugar solutions in water, he gets out an estimate of Avogadro's number. That's the dissertation, and that's the thing that he got his PhD for. I'm just curious. I know some of you know this. it isn't used to some of you, is it? Is it not, or do you all?
What news?
That Einstein did this, and that's what he got his PhD for. Yeah, it is. I'm just trying to figure out if I'm completely disconnected from what people know.
As far as I looked at that history, I had the distinct impression that Einstein and his professor were not on very good terms.
Yes.
And that his professor objected to all of this radical new stuff that he was thinking about. And he rejected an earlier version of the dissertation, an earlier dissertation manuscript, which is not, there's no copy of it left. Nobody knows what's inside it. And that Einstein at some point was so desperate to get his PhD that he just produced a non-radical, good old-fashioned type of stuff, paper, especially for the purpose of getting the permission or the approval.
All right, okay, you're getting ahead of the story, so I'll be talking about that just a little bit, right? Okay, so let's move on from there. So how did Einstein think of these pages? Well, it's hard to tell. We don't have too much from the period. There's this letter that Einstein wrote in May of 2005 to a friend of his, Conrad Harbish.
2005?
We call that a typographical error. Yeah. Yeah, that's interesting. Anyway, there it is. Read 1905. Right, just recalibrate. I work with a slightly different calendar from the rest of you. And so this is the letter. It's actually completely unreadable even to me because it's written in the old German handwriting. Einstein changed his handwriting style from one script to another just around this time. And you should understand this was a time in which politeness and formality were at a premium. So so even in letters you spoke in accord with the time. So I'm just calibrating you so that when I tell you what he said, you'll realize. He says, "So what are you up to, you frozen whale, you smoke-dried canned piece of soul? Why have you still not sent me your dissertation? Don't you know that I am one of the 1.5 fellows who would read it with interest and pleasure? You wretched man. I promise you 4 papers in return." And then he goes through describing which the papers are. And I'll leave the first one for a moment because that's going to be the point of this. He says the second paper is the determination of the true sizes of atoms from the diffusion and viscosity of dilute solutions of neutral substances. The third proves that on the assumption of the molecular kinetic theory of heat, bodies of the order of magnitude of 1/1000th of a millimeter suspended in liquids must already perform an observable random motion that is produced by thermal motion. The fourth paper is only a rough draft at this point and is an electrodynamics of moving bodies, which employs a modification of the theory of space and time. The purely kinematical part of this paper will surely interest you. Right? So I read through all of that to calibrate you for what he then says about the first paper. The first paper deals with radiation and the energy properties of light and is very revolutionary. Right? So what I'm going to talk about now is the one thing that Einstein identifies out of that year as being very, very revolutionary. So let's get a sense. Why does he think that it's very revolutionary? All the other papers are in effect working out themes that had been developed in the 19th century. You can, at the courses level of description, which I will now go into, each of the papers is bringing closure to something that had been developing through the course of the 19th century. And we can just go through the cases and you'll see how that works. What he's doing in the doctoral dissertation and the Brownian motion paper is he's sealing the deal on the molecular kinetic program of Maxwell and Boltzmann. He's producing a phenomenon, right, that cannot be handled unless you go to the molecular theory. Up until then, you heard, who was talking about Planck? Was it, yeah. I mean, there was the sense that you didn't need, right? Molecules may be that we just don't need them. We can do everything we need to do thermally in the lab just by using ordinary thermodynamics. Here now was a phenomenon that you couldn't handle that way. This is the Brownian motion paper, and I'll be talking about that a little bit more. I won't say much about special relativity, but those of you who work in the field will realize that there's a sense in which special relativity is in electrodynamics. I mean, the Lorentz group is already in Maxwell's equations, and Lorentz has pulled it out. And it's just a matter of, the effects that we think of as relativistic, length contractional time dilation, local time, which becomes the relativity of simultaneity. It's all in there, and it just takes someone to pull it out as a kinematical theory and repackage it. And so it is, as it were, the deeper moral that lay hidden inside special relativity. And there's a similar thought for A equals mc squared. There are electromagnetic waves carrying energy and momentum, and you're starting to get the sorts of relations appearing that are generalized by Einstein as E equals mc squared. So he's pulling it all together, but not with the light quantum. The light quantum paper is a very different beastie. So where all the rest are developing or completing 19th century physics, what Einstein's about to do is to overturn what seemed to be the greatest achievement of the 19th century. The great theory at the end was the Maxwell-Lorentz theory of electrodynamics. It had become, nowadays we talk about a theory of everything. It had become a candidate for the theory of everything. Right? So, in the course of the century, you'd seen the wave theory of light, Newton's corpuscular theory fade away, the wave theory had taken over, electrodynamics had absorbed the wave theory of light, and people were thinking all matter is somehow electrical or electrodynamic in character. The wave theory of light is reigning supreme at this point. It's right at the middle of the most successful physical theory of the era. It says light is waves. Well, now Einstein in 1905 is now contradicting that. He's saying, well, not always. Right? And he says, no, he says sometimes, and then out comes the beautiful, simple clause, such as could be found in a used car sales contract. Monochromatic radiation of low density behaves as long as Wien's radiation formula is valid in the thermodynamic sense as if it consisted of mutually independent energy quanta of magnitude h nu. Right, that's the light quantum hypothesis as it appears in the paper. More loosely speaking, he's saying light behaves as though its energy were localized in mutually independent points in space, spatially localized, with an energy of h times the frequency. Of course, you know what happens next. This is now the beginning of something that, to this day, if you ask someone what is a light quantum, it's still difficult, right? Just to get clear on exactly what the ontology of this theory is. Okay, so where am I going with this? Well, I want to make a few points. There are going to be a few models. And one of them is going to be, I think maybe the major one, is going to be something in sort of history and methodology. Given the build-up that I've just given you, you can see that the content of Einstein's discovery of the light quantum is really unanticipated, extraordinary, I'd even say foolhardy. It was just, you're overturning the most successful theory of the time without really much apology. You just bang, lay it all out. You're saying high frequency light energy exists in spatially independent, spatially localized points. So the content is very striking, quite extraordinary. But that's not what I want to talk about. I think that's the wrong way to think about it. There's another way to think about it. You can think about the methods that Einstein's using to discover this stuff, right? And it's very, very different what those methods are, right? You can see when you what I'll be tracing out as the pathway for you. You can see that Einstein's proposal of the light quantum actually fits into a coherent research program that was really flourishing in 1905, and it was based on one very simple problem, and that is, you're given what we see of matter macroscopically, right? And you want to figure out what is its microscopic constitution? Right, that's the problem. We see this macroscopically, what's going on microscopically. That's Einstein's program. And it's very well worked out by 1905. He's got a good repertoire of techniques. He's invented a lot of his own statistical physics in order to handle it. And what he then does is he applies those techniques to radiation. Right, that's the trick. So I'm getting ahead of the text here. So the common theme in the statistical papers of 1905, the Brownian motion paper, the dissertation, is that he's looking at thermal systems that consist of spatially independent, spatially localized points. They might be little corpuscles, Brownian pollen grains, or they might be little sugar molecules, but they have that key property. And in case you haven't seen the connection, it's the same guy. Right? And it's not a coincidence that it's the same guy, because he's figured that out. Right? He's figured out their properties, and he's nailed them down by using a repertoire of techniques that he then applies to radiation. Right? So, and I'll say that for me personally, why do I do history and philosophy of science? I'm very interested in discovery. I'm interested in how people with just ordinary tools, ordinary access to the world, the same access that I have, are able to discover extraordinary things. Right? And so this for me is kind of core interest. When I first started working on general relativity, it was the same idea. You want to?
Yeah, well, but I'm perfectly sympathetic to what you're saying, but isn't it true that the paper on the sugar solutions and Brownian motion were actually later?
Oh yeah, no, the dating was later.
Yeah.
Yeah.
How can you say he had already worked out this successful research program when he started to apply it to radiation?
Well, we're getting ahead, but just briefly, what I'm going to argue is that a lot of the stuff he already had in place well before. And if you go back to the papers in 1901 already, you see the techniques that he's using developed there with greater care. But yeah, no, I agree. It's an awkwardness that they're a few months apart. But look, the guy was just cranking stuff out.
Yeah,
I don't know about you, but it's quite possible to sort of finish one manuscript and then come back to it while you send off another, and then go back to the first and send them off. The guy had a full-time job at the patent office, and he well, all right, enough said. So here's a picture just to get the contrast a little more clearly for you. So if you locate Einstein's light quantum paper against the background of electrodynamics, that project that interests me so much of understanding how someone can discover extraordinary things by ordinary means, right, that just becomes unintelligible. Right? But if you locate it against the background of Einstein's work in statistical physics, then it becomes intelligible. Now, it doesn't become ordinary, right? What Einstein does with the light quantum is still, completely amazing and inspiring, but it's not magical. Right? You can understand how it works, and that's what I want to do. I also want to point out fluctuations. Einstein is often described in statistical physics as the master of fluctuations, and you're going to see a lot of that fluctuation analysis being done here. And I mean, fluctuations are tremendously important. These are the deviations that statistical systems manifest from average behaviors, and those average behaviors coincide with the normal thermodynamic behavior. So the fluctuations, insofar as you can see them, are showing you that the ordinary thermodynamics is inadequate for the phenomena that you're dealing with. So what I just said is a fancy way of saying why we need atoms and not just ordinary thermodynamics. And I'll be talking a bit about the methods and ideas that he introduces. Okay.
I think the other reason we need atoms is because we want to understand microphysically why they state what they are. So.
Yeah, yes. And, I mean, in the explanatory project, if you want to explain why things manifest to us the way they do, you will need to use an atomic explanation, as opposed to doing what Planck hoped you could do, and that is say, well, there might really be atoms there, but they're inert when it comes to explanatory powers. And I think Oswald had a similar attitude. Right? I mean, what's always struck me is how rapidly Ostwald's flipped after Brownian motion came out. Okay, so I want to try and get the bigger picture of what Einstein was up to. So I want to talk about Einstein's first two worthless papers. Here again, I've got a mixed audience. Some of you know this stuff intimately, and some of you may be seeing it for the first time. Einstein did not start publishing in 1905. Right? By 1905, he was already a well-established author in the literature. He published a series of strong papers in an arm de physique. I don't know, he would certainly not assign the word strong to these. His first two papers, I've given you the first 2 pages here. This one is called Conclusions Drawn from the Phenomenon of Capillarity, and this one is, I won't read through the title, but it's all about dissociations of metals and molecular forces. Now, these 2 early papers, in Einstein's own judgment, were worthless. This comes from a letter that Einstein wrote to Stark in December of 1907. Got the century right on that one. In which he was sending papers to Stark, and he simply said, "I'm sending you all my publications, excepting my 2 worthless beginner works." Right? Well. I suppose if you're an Einstein, that might be a good assessment, but for anybody else, these weren't bad papers. Here's the project. All right, this is the beginning of that, the beginning and publication of that project of trying to figure out the inner constitution of matter from its macroscopic properties. Now, the particular model that Einstein had in mind was a fairly simple one. He used Newtonian attractive forces as a kind of as a template, and he imagined that there's a force between 2 molecules which is governed by potential of that particular form, and there are 2 undetermined constants, C1 and C2, belonging to each of the 2 molecules, and the goal was to figure out what those constants are. Not a tremendously exciting project, right, in terms of the result. And he was trying to use the phenomenon of capillarity. You know, when you have a thin glass tube and you put water inside, the water rises up and it forms a meniscus. And he's looking at that sort of behaviour as the meniscus is dragged up by the glass, and he's looking at that sort of behaviour as a way of getting hold of these constants. But there you see the move, and then he's doing a similar thing with electrochemical potentials, with molecular dissociation of solutions. All right, but there's like, whoa! But what's in there that's important, right? And not the particular results. Right? He was right. There was no longevity in any of the results that he got. In fact, he was so dissatisfied at the end, I think, of the second paper, he writes a little apology to the reader for how poorly worked out everything is, and how he's done no experimental work. But what he has done, right? But what he has done is to develop the machinery that we're going to see coming back in 1905 for dealing with dilute solutions. Particularly, he developed a very simple technique for dealing with osmotic pressure. You know that if you have a dilute solution, it exerts an osmotic pressure on a semi-permeable membrane. Well, Einstein decided there was something fishy about semi-permeable membranes, and he just didn't want to deal with them. And so instead, he said, I'm going to give the same analysis, but not use membranes, I will use force fields. Right? Fields that selectively act on the different species in solution. And that technique of balancing osmotic pressure against a force field is going to come back as a core piece of what Einstein does later in 1905. Okay, the next 3 papers, however, were more impressive. Einstein clearly felt that he needed a better understanding of statistical physics than he had, and he goes on to write papers just on simple things like, kinetic theory, second law of thermodynamics, and these are the 3 papers. A theory of the foundations of thermodynamics is the second one, and then the third one on the general molecular theory of heat. Crudely, loosely, people describe this as an independent discovery of the Gibbs formalism, and I think that's zeroth order correct, right?
Oh, yes.
Yeah. Einstein's own remark was that he hadn't known about Gibbs's work, and when it was pointed out to him later, he said, had he known of Gibbs's work, he wouldn't have published it. Right? Well, I guess if you're Einstein, you can.
Well, yeah. In some respects, it's better than Gibbs.
Oh, is that right?
In certain other respects, it's not. But,
Okay. You'll be talking about Gibbs later, right?
Yeah.
That's why I'm sorry that you didn't get to the Gibbs stuff. There's a lot in here, but I want to point to one particular element that he introduces in 1904 for two reasons. First, it's a part of the story, although we don't know exactly how it fits in. But second, it's a particular calculational technique that I just think is under-recognized. It's a very simple trick, but it's incredibly powerful. It gives you wonderful results. So I call it the hidden gem. And it's Einstein's fluctuation formula. Let me take it a little slowly so you get the moves, because there's so little in it, and you get so much out that it's really quite wonderful. First, I should just advertise something. Everyone who stood here has tried to tell you if you know nothing else, what's the thing that you should know, right? And it all depends on where you stand, what sort of calculations you want to do. Now, my answer to that question is different from everyone else's. If you know nothing else in statistical physics, whatever, right, you need to know this, right? I find that if you know that, you get a very rapid entry to a hell of a lot of statistical physics. Now what does that say? It's the formula for the canonical distribution of Gibbs, or the Boltzmann distribution. It says the following: if you have a system that is in thermal equilibrium at temperature T with another system, with a larger system, then the probability that that system happens to have energy E is proportional to that exponential factor. Right? There's a hell of a lot in that. You take that as a starting point of a calculation, and you can go a very long way indeed. So it applies to everything in this room. Yeah?
There's some state counting factor you need too. So there's probably one particular state with energy E, but there might be multiple states with energy E.
Well, you're getting ahead of me. The key thing, I very carefully put a proportionality factor in here, because you then have to normalize it. And there's a hell of a lot of, and the normalization is done with the partition function.
But I'm saying it might not be a constant at the front. It might be a function of E at the front, because the states might
It's the density of states.
better with E.
There's more in that. It all goes into that one guy, right? That normalizes it. And yes, no, I agree. There's just a proportionality constant that you need that other guy, and it does a hell of a lot of work. And that partition function that you want to see stuck in there, just hitting that with differential operators gives you all of your thermodynamic quantities.
And we're saying it's not just a prediction function, which is a constant. There's a non-constant density of states there.
If the density here is over E, yes, you'll need an extra guy.
Well, that's what you wrote. You said the probability that it has an energy E. So so if you want to say probability has a given state, and that state has energy.
Agree. Yeah. I've left vague what the probability is over, but you're exactly right. If the density is over the energy continuum, you need an extra guy. I agree.
What we want is for base P of x is proportional to e to the minus P of x over k. Where e is the energy of the state x.
All right. I prefer to write that way, but that's fine. Anyway, so all right, so you start with that guy, add in all of his concerns. It's just a probability distribution, so it's going to have a variance, right? And so it's going to have a mean, it's going to have a variance. Let's calculate them. This is the mean here. This is E bar, and this is the variance, which is defined as the mean of the square deviations from the energy mean. And what Einstein shows, it's not a hard calculation. What Einstein shows is you get this formula here. Now, the interesting thing about this dE bar dt is that that's the heat capacity the system. It's the sensitivity of the mean energy of the system to temperature, right? And so this expression reduces to kT squared multiplied by the heat capacity. So what you have here is that the variance in the energy distribution is determined by quantities that are all equilibrium quantities. Right? So this is a bridge that takes you from equilibrium quantities up to up to the thing that distinguishes molecular systems from ordinary equilibrium thermodynamic systems. Right? So let's see where we go with that. So here, just because I like the history, here's Einstein writing it down, and I'll just read what he says here. The magnitude epsilon squared bar is a measure for the thermal stability of the system. The bigger that epsilon squared bar is, then correspondingly smaller is the stability of the system. Right? Okay, so what do you do with this? I'm going to work through a simple calculation with a very particular reason in mind. So let's say you're interested in an ideal gas. I'll take an ideal monatomic gas of n molecules. We know that its mean energy is given by 3 nkt over 2. Nothing terribly fancy there. And so the heat capacity is 3 nk over 2. We've had closely similar results from I think, David, you had some stuff like this up there. Okay, so what are the fluctuations? Well, it's, all the calculations are right there. It's very easy to calculate. You get, this is the Einstein fluctuation formula. You plug it straight in, and you get that the root mean square of the fluctuations, which is just epsilon, as a fraction of the mean energy, is given by this term in roughly 1 over the square root of n. So if you're looking at a macroscopic monatomic gas, you're going to have 10 to the 24 atoms, typical sort of, it's monatomic gas, so 10 to the 24 molecules atoms, so this will be very small. But if you're looking at just one of these guys, then the fluctuations will be big. Nothing surprising there, it's exactly what you thought, but boy, very easy just to write down the results without having to think terribly hard. But remember what I said earlier on, very, very little goes into this, right? It's simply the idea that you have a canonical distribution that's exponential dependent. So you can apply it to any system you like, right? And just crank the handle and see what comes out. And that's what Einstein does in the final paper of the series, of the 1904 papers. He says heat radiation, right? Well, heat radiation is, it's a thermal system. Just imagine it, just a box with hot walls, an oven, a potter's kiln. It's going to be full of radiation. Right? We know how much energy is in the radiation. Right? This is work that's been done through the 19th century. The energy, mean energy here is proportional to the 4th power of temperature. So now we know what the heat capacity is. Right? And so we can start to turn the wheels. Now, I just want to stress here that the audacity of doing this is being done at a time when it was really very unclear exactly what the constitution of radiation was. Right? This is, Planck has done something in 1900 that if you knew how to read him would suggest that maybe there's something weird going on. Einstein clearly knows there's something weird going on. The light quantum paper of the following year is going to nail it very precisely. So this is pretty bold. He just says, he trusts in his formula. He does the calculation, and then out comes this result here, and you get a 1 over t to the 3 over 2. Now, what happens next? I'll just tell you briefly what happens next. Einstein then says, so we can now figure out which volume, right, of radiation is going to give us the most fluctuations, right? And then from that, by an argument that I sometimes understand and sometimes lose, he ends up with the Wien displacement law for radiation. He gets pretty good, approximation for a known result. Now, I don't want to say too much about this. This has been a focus of much interest for historians. because there's something going on here that is important. Right? Einstein is looking at fluctuations in radiation, and as you see when we start talking about fluctuations in radiation in 1905, they are the key thing that is the tip-off for the light quantum. So Einstein is sort of getting really, really close. Right? But, and there have been a lot of conjectures as to exactly what's going on here. I don't know that I believe any of them. I think they're all stretching. I think we just need. I think the best we can say is he's onto something. He knows he's onto something, but we don't know what. And just step back and just look at the extraordinary power that he's gotten from his formalism. He can now tell you, even though no one has observed, right, the fluctuations in radiation, he can tell you how big they are. Right? He's got a you know, really quite firm control of that without actually knowing anything reliable about the inner constitution of radiation. Okay. All right, so let's move on now to Einstein's doctoral dissertation. This is the work that's normally neglected. I want to spend a bit of time on it because Einstein's logical pathway goes right through the middle of this. You'll see what I mean by that in a moment. This is the work as it came out. It was published in 1905 as a separate inaugural dissertation. And then it was republished the following year in an Annales de Physique as a separate journal article. What's the project? The project is in line with the stuff that he'd been doing since 1901. He wants to figure out what is the inner constitution of matter, and he's decided that he's going to just nail down the magnitude of what in Germany is known as Loschmidt's number. When I was taught this stuff, it was called Avogadro's number. I don't know what it is in Canada. Is it
Avogadro's number.
Is it Avogadro's number? Okay. What is it in the Netherlands?
I forgot.
Avogadro. That's interesting. Here's the basic idea. Right? The basic idea is that water has a certain viscosity, right? Certain, it's sort of goopy, and certain resistance to flow. If you dissolve sugar in the water, it starts to get syrupy. Right? Now, by the time it's looking like a syrup, you're well out of the regime that Einstein was interested in. But when you first add those first few crystals of sugar and you have a dilute sugar solution, the viscosity has increased, it's already started to thicken. Now, what's the mechanism that's doing the thickening? Well, when you try and get that water to flow through a little orifice, right, as all the water comes down, then those molecules are unforgiving. The water has to flow around the molecules. And so it's this obstruction to the flow of the water around the molecules that is increasing the viscosity. It's making it harder to drive the sugar solutions through. Now, it's not the sugar molecules hitting each other and blocking things, because Einstein's dealing with a case of a dilute solution. And in the dilute solution, you assume they don't hit each other. That's the effect that he wants. And so he's got to, if you're thinking about it, try and set up equations of fluid flow that are going to deal with that particular problem. It is not an easy thing to do. What Einstein does is he goes through a whole bunch of changes of frames of reference, moves to co-moving frames of references that move along with with an individual sugar molecule, and then the whole thing reduces down to solving this flow problem. This is the last part of the flow that he can't, as it were, transform away or handle easily by tricks like that. You have a component that goes in and then spreads out again. I've drawn the picture here, so you can see this is the sugar molecule, which is idealized as a perfect sphere. And those of you who know what the molecular structure of sucrose looks like, you'll realize that's, well, maybe, right? There's a parameter p, which is the diameter of this particular sphere. Okay, so that's the problem that he's working on. And when you look at Einstein's paper, you realize, God, this is complicated. It is a long, hard, tedious, difficult paper, right? And you grind through, and you get all of these special assumptions keep raining down out of the sky. Okay, sugar molecules are spherical. Actually, I wonder if that, there's this joke where the physicists, oh, never mind. The punchline is assume a spherical cow. I wonder if that's, yeah, I want to vacuum home, that doesn't work. But anyway, so he's got the spherical cow here, right? And, it just keeps going, it just grinds away. And it is, I've read a lot of Einstein. It's a painful read in a way like nothing else that I've seen. Maybe it fits with Yoss's image that he just had to get the thing out. He gets this result here, which I'll come back to in a moment. All I want to point out is that it wasn't just me who was having trouble with it. Einstein was having trouble with it as well. He's actually got the wrong result, right? And he's off by a factor. There's a factor that's going to be needed in the formula here of 5/2, and he doesn't realize it, right? He doesn't realize that the factor's wrong. The examiners don't realize it. The thing gets passed. He gets his PhD, and it's only a few years later when the experimental results come in, and people are starting to measure how the viscosity of sugar compares up with Einstein's prediction, that they realize there's something wrong. Einstein's unable to find the problem. And my best recollection is that he gives it to Hopf, his assistant at the time, and Hopf finds the problem. So yeah, having just gone through that story, Joss indicated something I wanted to tell you about. This was not the first attempt, right? This was a later attempt. There was an earlier work that Einstein submitted that got turned down, and I've always thought, how do you feel if you are the guy who turned down, right, Einstein's dissertation? You say, look, Albert, it's a nice piece of work, but it's just not good enough. We have standards here. We can't accept this.
Oh, look at me, those are
but then when I read through this, and I'm just saying, well, if this is the cleaned up, improved version, I mean, we have no idea what was in the earlier version. We don't even know if it's on the same project. But maybe it wasn't so clear cut. Maybe the earlier decision was, So what's the result? The result is a very comfortable result, just the sort of thing that you would like to see. The apparent viscosity is equal to the viscosity of pure water multiplied by 1 plus the fraction of the volume taken up by sugar. Right? So you just geometrically look at the fraction of the volume that's taken up by sugar. That straight away gives you the factor that you multiply the pure water viscosity by to get the final viscosity. You can see why he could miss this factor of 5/2 because it's such a simple and nice formula. Now, the thing I want to point out is this factor here of phi contains, you want to figure out what that is, so you put in things like the density of the sugar, the molecular weight of the sugar, and then you've got Avogadro's number, Loschmidt's number, and you need the p's. Just go through it. It's a simple, trivial calculation. You just go through it. So you've got, in effect, you now have a whole bunch of quantities that you know. The apparent viscosity, the measured viscosity of a dilute sugar solution, viscosity of water, and then you have terms in N and P. So what Einstein now does is to take that equation and turn it inside out, right? Because remember what his target is. His target is to get to Avogadro's number. And the idea is that he's going to use existing data on the viscosity of sugar solutions, right? Why sugar, by the way? My understanding has been that it's because sugar's not a polar molecule. You wouldn't do it because then you get further, you get further problems. And I'm also guessing that sugar solutions are probably something for which there was a huge repository of data already, which I think, by the way, is one of the unspoken engines of the birth of thermodynamics around 1850, right? Because there were steam tables, very elaborate steam tables, available for the builders of steam engines. And so, if I remember correctly, Thomson is drawing heavily on, there's a Frenchman, Raynaud. Yeah. So anyway, so all these interconnections. Okay, so you've got all these measurable quantities, viscosity there, you've got unique densities and so on. But there's a problem, right?
John, wait, oh yeah, okay, never mind.
Oh, what?
I was about to ask that.
Well, that was the problem. So you can see here, Einstein's project has stalled at this point. Because in order to know Avogadro's number, which tells you how big molecules are, you've got to know how big that guy is, which is the radius of the sphere that idealizes the sugar molecule, but of course you don't know that. So you've got the classic problem that bedevils everyone trying to solve these things. You've got one equation and two unknowns. So what does Einstein do? He is nothing if he is not persistent. He just goes back to the drawing board and says, well, if I've done it once with viscosity, I can do it again, right? I've got to find some other property of sugar that will let me get a relation between N and P. And so he makes the move that is going to be the critical one for going forward. He says, well, I've got data on the diffusion of sugar in water. I'll come back to where this comes from. But it's the classic thing. You have a cup of water, you put a little bit of sugar in the bottom, right? And over time, over a long time, that sugar will gradually diffuse through the water. Right? It's just the process of diffusion. Right? On the molecular scale, the little sugar molecules are sort of bouncing around, gradually spreading out through the water. It's a diffusion process, so it's governed by the standard equations. There's a coefficient of diffusion, which is this factor D here, which is it's a measurable quantity. It tells you it's just the ratio between the gradient of the sugar concentration, right, and the rate at which the sugar transports. It's a standard factor in mass transport theory, and one that's readily measurable. Although I don't quite know what the techniques are. Okay, so now he's gotten those two together. He now has two equations, right, in two unknowns, so he can solve them. And of course, he solves it, then he gets the wrong answer because the first equation was wrong. So the initial value for Avogadro's number is 2 by 10 to the 23, and it's later corrected to 6.6, which is it's off by about 10%. Okay. So now I want to look a bit at the statistics of dilute sugar solutions. The process here is to gradually move from the ordinary familiar to the less familiar. That's the strategy. So Einstein has to give an analysis of the properties of sugar in dilute solutions. And what he notices, and I'll give you the details of this, but I just want you to get the punchline here. What he notices is the following. An adequate model for a dilute sugar solution is that you have a large number of these spatially localized sugar molecules that do not interact with one another. That's the import of the diluteness of the solution. They're not interacting with each other, okay? But they do exert an osmotic pressure, right? And to figure out what that osmotic pressure is, you can use exactly the same analysis as you can use for an ideal gas, because that crude description that I just gave you is also the microscopic description of an ideal gas. It consists of very many molecules that don't interact with one another. Now you tend to think that you follow the Bernoulli model that Jos talked about. You tend to think, well, to get the PV as nRT relationship, you've got to have the molecules flying freely to and fro, right, through the space. Otherwise, you're not going to get that. But no, it turns out, and I'll show you how it's done. It turns out that you don't need to do that. You can get the ideal gas law just out of this assumption. What matters is only that these sugar molecules are spatially localized, right? And they don't interact with each other. But they can have all sorts of interactions with the fluid around them. That isn't going to affect things. You will get the relationship for osmotic pressure out, which matches the ideal gas law. And I don't know about you, but I had to take a physical chemistry class once, and I can remember when I was just told that osmotic pressure obeys the ideal gas law. And I remember thinking, well, where the hell did that come from? It just sort of fell from nowhere. And of course, it was never explained. You just told this. Everyone knows that. And I thought, well, it doesn't make any sense. Why would it? Well, this is the reason, and and it's built in. Okay, so now how does Einstein get that diffusion equation that I described earlier for you? He uses the device that I described for you as coming out of his early papers of 1901 and 1902. He doesn't, that, I had a picture here of a semi-permeable membrane. He hasn't got that. That's just me, just helping you make it familiar, right? This is the normal picture that we get. This is a membrane that passes water but not sugar, right? And so the sugar molecules are going to hit the membrane and exert a pressure on it, which is held down by that weight, right? So that's the normal picture. But that isn't how Einstein does the analysis. He uses his own techniques. He says that the diffusion rate can be recovered by noting that you can set up an equilibrium. Right? There are going to be, have sugar in solution. Right? There are going to be two processes at work. One process is the force of gravity, that force field that I talked about earlier on. Right? The force of gravity pulling the sugar molecules, the spheres, down towards the bottom, and they're going to fall according to, with a resistance given by Stokes' law, so you can figure out how fast they're falling down. But of course, the sugar doesn't separate out and collect in the bottom because there are diffusion forces that are really very strong on these scales that are shoving everything back up again. Osmotic pressure, if you like, is shoving everything back up again. So you'll form a density gradient. That the diffusion will shove things up the density gradient, set the two quantities to equal to one another, and out comes the condition for the perfect balance, which is that equation that I showed you earlier. Okay, you get the idea? So you see in these papers a large battery of techniques for doing things. Right? And we're just going to see these techniques used and reused again. So now we can turn to the Brownian motion paper. Now I should just clarify here. There's always an equivocation on why the Brownian motion paper. Einstein in the paper predicts that very small corpuscles will move in these random jiggles and gives a very thorough analysis of them. He doesn't know that this is the same as Brownian motion. He knows that Brownian motion is the motion of pollen grains that the botanist, I can't remember his first name, Brown, saw in the 19th century. Right? And people were sort of conjecturing, maybe it's thermal, maybe it's not, who knows. Einstein knew of Brown's observation, but he didn't have enough data to know whether it was the same guy. Obviously, it turns out to be the same guy, but he didn't know that at the time, and so he just poses it as a question. In the paper itself, and so here's the paper. I don't know if this is the page where he talks about Brown. Yeah, here's Brown. Yeah, he says it's possible that the motions treated here are identical with the with Brownian molecular motion, but he says he hasn't got enough information to figure it out. All right. Okay, so where does this come from? Well, this is a conjecture. Einstein never says this. But sometimes conjectures are so appealing that you say, well, if that isn't right, I don't know what would be. Right? Let's just go back to the awkwardness of Einstein's doctoral dissertation. Right? Remember how the guy had to fight and struggle to get results. He needed two separate analyses. Right, in order to get two relations between two quantities, right? And the whole thing is fraught and complicated. Unbeknownst to him, there was a mistake in it. Wouldn't you want to simplify this if you possibly could? Right? Wouldn't it be just wonderful? I mean, how could you simplify this? Well, let's look at the two unknowns. One is Avogadro's number. The other is the radius or the diameter. I don't remember which of the sugar molecule. Wouldn't it be so wonderful if you could just look in a microscope and actually see, right? Actually just see how big this thing was. Well, do you have to use sugar for this analysis? What would happen if you just applied this analysis to little suspended corpuscles that were so big you could actually see them in a microscope? Well, then everything would get very simple, right? Because you wouldn't need two equations. You could use whichever of these equations you like better, right? And so that's the move. Right? Einstein says, let's just take this. I paraphrase Einstein as saying, let's just take the analysis I gave you and just apply it directly to a system of corpuscles whose size p is visible microscopically. And then all Einstein needs to do is to replicate the second analysis that I gave you on diffusion, right? And you get the Brownian motion paper. So you see the logical progression there. Now I don't know for sure if that's exactly how it happened. We don't have sources. There's the awkwardness that Jos pointed out. They're separated in time with the dissertation. I think
Just a few weeks.
it's just a few weeks, but I think there are references between them, so
Yes.
so they're being written together. Anyway, but for my purposes, what I want to point out is that the same analysis can be done. Einstein points out quite correctly that even microscopically visible corpuscles in a solution are going to be subject to exactly the same thermodynamic analysis as he gave for sugar molecules, and as a result, they're going to exert an osmotic pressure, right? And you can use that osmotic pressure to determine the way that they will move and diffuse. Okay, so notice we have two levels of description here. You can describe things at the molecular scale or the corpuscular scale as, you know, the corpuscles are located over here in solution, and because they're moving randomly, they spread out, right? And they will actually apply, they spread out. I almost made the step to the end. Then there's a second description in which you just, think of them think of them on the level of their average behavior. They will exert a pressure as they're spreading. Einstein's jumping backwards and forwards between those two descriptions, but the analysis stays the same. You get the ideal gas law obtains for them, and you get this, and you get exactly the same relation as you had for the sugar solutions. And so now the exercise has become very simple. All he's got to do is figure out what this diffusion coefficient is. Right? And once you know the diffusion coefficient, then you can nail Avogadro's number. And that, of course, that's the big result. Then he gives the correct result for Avogadro's number. But now you've got a problem. How, for these small corpuscles, how do you determine what the diffusion coefficient is? This was a pretty good year for Einstein, because in order to do that, so I'm jumping ahead of myself here. That's the motion that you will see. Okay. I missed the most important part. This is in the early part of the paper, right? When Einstein is predicting the results that he's going to have, and he just says this. He's predicting that these corpuscles will produce random motions that are going to be visible under the microscope. Right? That turns out to be Brownian motion. And he says, if it is really possible to observe the motion discussed here, then classical thermodynamics can no longer be viewed as strictly valid, even for microscopically distinguishable spaces, right? And an exact determination of the real size of atoms becomes possible. So he's here announcing the end of the strict validity of thermodynamics. This is Einstein's first statement of it. Okay, but now let's go back to where I was before. Einstein needs to figure out how to attach a diffusion coefficient to that motion so he can use the apparatus that he developed for the diffusion of sugar. The trouble is, it's not sort of fluid that's expanding. You can measure the diffusion of sugar by measuring sugar concentrations over time. So what do? Well, I was starting to say before, it was a good year for Einstein, and so indeed this was the year in which he laid the foundations for the modern theory of stochastic processes. Right? And so what? This is the. I take it's the first version. I don't.
There's Markov, and it's almost contemporary.
Yeah.
And it is.
Anyway, never mind. It's early. But this is one of the early, and I suspect the earliest, but I'm not sure, instance of the random walk problem. So what's the phenomenon that he's got to deal with? Well, you start out with one of these corpuscles located at time 0 somewhere in the suspending fluid, right? And then you let time pass and see what happens. Well, its position is going to spread, and it's going to spread out on a bell curve, on a Gaussian. And the result that he gets by laying out the elements of this theory is that the variance of the bell curve is given by 2 times the diffusion coefficient multiplied by the time. So if you want to get at that diffusion coefficient, it's a quite easy thing to do. You just start out with with particles in suspension, and then just track their motions, fit the bell curves, and figure out what the variance is. And then you can then plug that diffusion coefficient into the equation here. You know what the P is because you're seeing these things under a microscope, and then out comes Avogadro's number. I'll just mention 2 things. If you've not played around with these things, there are a couple of just a couple of traps that you just need to be warned about. So if you're seeing this for the first time, let me just give you a warning. One of the mistakes people made when they first looked at Brownian motion was that they wanted to figure out how fast it was. What's the speed with which these little pollen grains are moving, right? Well, it turns out there is no speed, right? The problem is that the displacement, the distance they're going, right, is proportional to the square root of time, right? So they're moving out the bell curve. The spread of the bell curve, the variance, is proportional to time. So the measure of that spread is going to be the square root of the variance, which is the square root of time. So that means that if you take the ratio of the displacement, how far the particle's gone, to time, you get something that goes to 0. Right? So efforts to determine the speed of Brownian motion were just misplaced. And Einstein had to correct this later in literature. People were trying to do this, and he had to write about that. Then the other thing is, I'm assuming you've somewhere seen what Brownian motion looks like under a microscope. And you see these guys jiggling backwards and forwards, and you're thinking, damn, hit by a molecule, hit by a molecule, hit by a molecule. No, that's not what's going on. In the course of 1 second, the number of collisions is enormous. Right? I don't remember what the number is for a typical ball grain in water, but something like 10 to the power of 11 springs to mind. There are huge numbers of collisions. What's going on is that your expectation that many collisions would average out to have no effect is wrong. That many collisions doesn't average out. You still get a motion that comes out of that. We're now going to start to move towards the light quantum. So I'm going to start to go through some of the statistical physics that makes the bridge. I've been pleased as I've been working on this stuff to see the same stuff popping up in the other presentations. So some of these formulae will be familiar. I'm drawing them straight out of Einstein's papers. So we're interested in this topic, the thermodynamics of fluctuating systems of independent components. Right? Now, of course, so far we've been talking about dilute sugar solutions. We've been talking about little corpuscles suspended in a fluid. But of course, the third case that we're moving towards, right? Fluctuating systems of independent components. It's going to be light quanta. So that's what we're moving towards with this. And it's not going to be quite as straightforward as I'd like. So this is how you handle exactly that system in the thermodynamics that Einstein, in the statistical physics Einstein was using in 1905. This is basically a Gibbs-style way of doing things. You have n spatially localized, spatially independent components. Right? So just the little sugar molecules or whatever. Yeah?
So is a function on the left a function of E, or is it in fact a function of pi 1 through pi n?
It is only pi 1. That's the point. Yes.
Pi 1 through pi n. Okay.
Yeah.
Right.
Yeah. That's.
It's a function of E, or like n squared.
That's what it says over here. So the way that you so we're faced with canonical momentum and position coordinates. The pi's are the momenta. the x's are the position coordinates, and we need to express the condition that the components are independent of one another. Now, nowadays we're very used to doing that with Hamiltonians, right? There's no spatial term in the Hamiltonian, as it were. There are no interaction terms there that have got the distances between them. We just don't want them to couple by their positions. Right? That's the key thing. And so Einstein represents that by saying that the energy, or the Hamiltonian, is simply a function of the canonical momenta and is not a function of position. Now, what's interesting is that I've kind of labored that. It's sort of completely obvious now to people who've survived 100 years of quantum mechanics. Einstein spent a page explaining why that was the right way to represent the non-interaction of molecules. I didn't see anything reading it that was especially revealing, as though there was something here, but apparently it was a sufficiently foreign notion that it needed a full page. So here we have the Boltzmann distribution that we started with all the normal qualifications about that proportionality sign needs work. One of the big results that you get out of the Gibbs formalism is that if you have a system that is canonically distributed in this way, right, so it is an equilibrium system and its probability distribution is given by this formula, then you can write down the entropy, the thermodynamic entropy of the system as this formula here, right? Okay, so when I say it's the thermodynamic entropy of the formula, I'm being very careful. It agrees with the Clausius definition. Remember, Clausius introduced the definition of entropy using the formula dq reversible over T, that changes of thermodynamic entropy were calculated by integrating along a reversible pathway in the state space, and you integrate dq over T. So you have that connection between heat and entropy that is essential in the equilibrium thermodynamics. This formula preserves that. And you're thinking, why am I making a big fuss about that? Well, just to look ahead, Jos has already pointed out how that connection gets broken when you move into a Boltzmann framework. There's a generalization to non-equilibrium systems, and you don't have that property manifested anywhere. Okay, so this is just a standard formula. If you go to any decent textbook in statistical physics, you'll find that formula. It's only specialized by the absence of the position coordinates in the argument for the energy. And so now you just do this integration. When you do the integration, the E over T term, mean E over T term at the front stays. Because there's no x dependence here, right, you can separate out the integration into a product of two integrals. Right? There's one that has all of the momentum dependence, right? Some big complicated expression there, no doubt. And then there's simply the integral with respect to the configuration coordinates, and then you've got the log of the whole thing. Okay? I think that's probably the hardest piece of mathematics I'm going to do. Yeah.
So I don't think I was clear.
Oh, what did I do?
I don't think I made my point clear before, but I think on the first line, shouldn't that read P of pi 1 through pi n, not P of E? And shouldn't it be the probability of those momenta, not the probability of the E?
Yes, you're right.
Yeah.
It's a
Otherwise, well, risk tested state.
What I was doing is I was doing what you complained about before.
Yeah.
I said the probability of energy. Yeah, okay. So just make that a probability distribution of the phase space. Yes, correct. Yes, you're correct. You're correct. I'm sorry. I was running on autopilot. I like to think of probability of energy, so I just plugged it in there. But yeah, that's a better way of reading it. I agree.
And the K is just that integral over the momentum.
Yeah. Well, you're now getting ahead of it. So we actually never need, or Einstein never needs to calculate what that expression is. Right? It's just some formula. It has no volume position dependence in it. Right? So it just becomes J. So this expression down here becomes this thing here. I think I've point that out. Yeah, there we go. Yeah. Okay. So they're only dependent on the momentum degrees of freedom. That's J. And this is the integral over all of the canonical variables in the configuration part of the phase space. So that's just the volume to the power of n for the system that's contained in some volume V. Okay, pretty simple stuff. And so that turns into this and this over here. And so the canonical entropy is given by expression in the mean energy and expression in the momentum degrees of freedom. And then, just to make sure you notice the importance, bing, right? So which one of you said this is the way you characterize an ideal? I think David.
Well,
yeah. I think you had. So I'm saying yes, good, but I see that again. so there it is, and this is Einstein doing it now. Okay, so how do you connect that to the more familiar form of the ideal gas law? Well, there's another quantity that Einstein uses. It's very Gibbs-like. So I was very pleased that you were giving Gibbs. There's a simpler expression that you get out amongst these canonical quantities, and that's just the free energy F defined as Yost here, and it's simply defined as minus kT. Logarithm of the integrated exponential. Go through the same calculation, and you get this result here. So the free energy, some term in the momentum degrees of freedom, and then nk, n the number of component molecules, k Boltzmann constant, t the temperature, log of volume. Right. So log of volume keeps popping up. How do we get to the ideal gas law in the familiar form? By the way, just endorse everything else said about equations of state. This does not exhaustively characterize the state. You do need to make assumptions about energy independently. So, but I'll bracket that out. You get there's a very simple formula for getting the pressure out of the free energy. This is just standard thermodynamics. You get it in any introductory text, so I won't labor it. You just take the partial derivative of the free energy with respect to volume. It's a very short derivation if you've never seen it. Not a hard thing to do at constant temperature. And take the derivative of the log of V with respect to V. You get 1 over V. It's pretty easy. And there's the pressure exerted by the components. You have the ideal gas law. Okay, so I want to pull out from here just how little has gone into this. All we have assumed is that we have a system of n spatially localized independent components. All right, that's it. They could be sugar molecules. Remember, I said I'd show you how this is done. They could be sugar molecules in solution. All right, we haven't asked over. We don't care about how they might be interacting with other things. That's going to produce terms that will not appear in the calculation here. Right? The part of the Hamiltonian that's giving us the ideal gas law is the part that says that their energy is independent of their position in the fluid. So you have so remember the bigger project. You're trying to figure out what is the microscopic constitution of matter from what you can observe, from what is measurable macroscopically. That's the project. Right? And so you've now got something really terrific. This is John Hancock, by the way, signature. Okay. You have the macroscopic signature of a system of n spatially localized, spatially independent components. Right? And so if you have such a system, it's going to manifest in these ways. The entropy is going to vary logarithmically with volume. More precisely, you're going to have the entropy is going to be some terms in energy and momentum degrees of freedom that you don't want to fuss with, and then logarithm of the volume, or by means of the calculation I showed you earlier, you'll get the ideal gas law out. I thought you might like to see this is Einstein's derivation of exactly these results. I don't know if you can see them here, but it's just I've just reproduced exactly what he has here. I think you probably see the ideal gas law popping up here, and this is from section 2 of the Brownian motion paper. right? So this is the apparatus for osmotic pressure that's being developed for a microscopically visible corpuscle. So Einstein's saying microscopically visible corpuscles exert osmotic pressure. Right? It's an illicit use of thermodynamics to do it. Okay, good. So now we're set up to move on to the miraculous argument. I call this the miraculous argument because, well, this is Einstein's year of miracles, annus mirabilis. Einstein himself pulls out one bit as being very revolutionary. So by his own judgment, there's this one thing that is really super duper. And then there's this one part of it that is, it's the main part, it's the big part, and it's a big argument. And so, because I'm a philosopher, I have an argument as a unit. And so I think of the miraculous argument. Here's the paper. I just like to show you the paper because I like reading original sources. That's always fun. Okay, so these are the sections of the paper. I split them out here for you. If you've never read this section 1, it is a very good read in its own right. I'll just advertise that. The hasty textbook account will tell you that in 1900, Max Planck realized that you could only account for the thermodynamic properties of heat radiation if you assumed that the energy of resonators is discrete, that it comes in steps of h times the frequency. Right? That might be a fair verdict or not. It's been a subject of tremendous debate amongst historians of science because Planck's papers truly are quite equivocal. My own feeling is I don't think Planck had any idea of just how big a problem he was glimpsing in these papers. I think he knew that there was something funny going on, but he figured he'd done enough in the papers, he'd have to solve every problem, and I don't think he had any idea that it was going to explode in the way that it did. This analysis here is, I think, a very good candidate for the first place where it's laid out in incontrovertible terms, that there's a really serious problem. That, I think, is Kuhn's verdict. Kuhn was the guy, Thomas Kuhn wrote a book on the history of quantum discontinuity. He was the one who first correctly laid out that the standard histories were getting much too quick. And he identifies this as the place. I think he might be right, but anyway. So that's that. That's worth looking at. Then there's this bit down here. This particular paper of Einstein is commonly known as the photoelectric effect paper because it contains the analysis for which he was awarded the Nobel Prize, or rather, sorry, he was awarded the Nobel Prize for a bunch of things like services to physics. But this was the one discovery that was mentioned in the award of the Nobel Prize. I'm not even going to talk about the photoelectric effect because it's such a minor part of the whole paper. What Einstein tended to do at this time was to give a long theoretical analysis, and then he would make a number of experimental connections. Very often they were predictions. Sometimes they were retrodictions, and typically he'd have 3. I don't know if you consult a PR person, but typically there'd be 3 here. So he's got 3. Stokes rule, photoelectric effect, ionization of gases. That all fit in with the light quantum gas. But that's pretty quick and pretty easy. The real work is what I want to talk about. The real work is what occupies this part of the paper. This is the development of the miraculous argument that I want to describe for you, how Einstein did this. So, okay, so let's go through the miraculous argument. It is wonderfully simple, seductively simple, beautifully simple. This is the page on which it appears, and let's now just tease out what's there. The first thing he does is to lay out a very simple piece of statistical physics. It's gotten so simple now it looks like a real snooze. Right, so let me just go through what it is. Let's assume that you have n independently moving points in some big volume V sub 0, right? N localized points moving independently of one another, right? Recognize the system, right? Now they're going to move backwards and forwards, and there's going to be some probability that they will all collect over at some moment in one side, right? And so the whole volume is V sub 0. The small volume in which they might collect is V, right? So the probability that just one of those points will be found in the smaller volume V is V divided by V naught, right? No mystery there. If you have n of them, the probability that all of them are over in one side is V divided by V naught raised to the power of n. It's sort of like coin tosses. It's really just elementary stuff. It could be molecules, it could be solutes in the solution, but easy stuff. Now comes the next thing, which I would just announce. There is a principle, Einstein says, called Boltzmann's principle, and I think you can help me, but I think it's named here for the first time. Yeah. So okay, so it's S is K log W. This is the thing that is engraved into Boltzmann's tombstone. It's actually named by Einstein. S is K log W. W stands for probability, Wahrscheinlichkeit in German, so that's why there are W's there. And so S is K log W. Apply that formula, and you get the entropy change for the process is S minus S0 is K log V on V0. Not a difficult calculation to do to plug the W into the formula. And then you complete, once you've got this, entropy varies with the logarithm of volume. I've already shown you how the way the calculation works, but there's not terribly much to it. Once you have that, it's then trivial to go down to the ideal gas law. So okay, so now you know this thing obeys the ideal gas law, and so it goes through that whole calculation. And so far, I hope you're recognizing he's really just reminiscing on the stuff that's in other papers. This has been handled by a much more detailed and much fancier formalism, and he's stripped it right down to something incredibly simple. But he's talking about stuff that is the content of the other papers of the period. So right, that's step one. Okay, so far nothing exciting. Now comes step two. These are the pages on which it appears. This is the whole thing. It's sort of remarkable that it all fits into that little bit of text. So what does he now do? Okay, what happens next is a little bit complicated. I've not put the formulae up. Maybe I should have. Einstein says, now let's think about heat radiation. Okay, now in particular, he wants to think about high-frequency heat radiation, and he wants to think about a system of high-frequency heat radiation that has its frequency inside a very narrow band. Right? That's the system that he wants to think about, and he wants to know what is the entropy of that system. Now, if you don't play around with this sort of thermal physics, you're saying, well, wait a minute, he wants to know the entropy of that system. That's fancy stuff, right? But no, it's not. If you're dealing with thermal systems, right, equilibrium thermal systems, figuring out the entropy of the system is just a bit of basic measurement. It's not a hard thing. It's not a hard thing to do. You get it from observations. If you work in physical chemistry, do any sort of calculation, you just have huge tables of these things, right? You want to know what is the entropy of this substance, and under these conditions, you just look it up, right? And it's the same deal going on here, right? Recall what happened around 1900. Lummer and Pringsheim in Berlin are doing more far-searching measurements of the energy density of heat radiation. Right? And you understand how easy it is to measure the heat density. How easy, you need fancy equipment and so on, but it's well within the powers of a normal laboratory to measure the energy density of heat radiation. You need an instrument known as a bolometer that can tell you how much energy is in the radiation, and then you can figure out how that energy density depends on the frequency and depends on the temperature, and then you put it all in a nice big formula, which is the one that Planck was working on in 1900. Once you know how the energy is a function of the temperature, it's a single derivation taking a single derivative, and you then just read off what the entropy is. All right? I should have written up the formula, but basically, well, I won't write.
So you mentioned Maxwell because he uses Bean's law, right? Because he's emphasizing high frequencies.
Oh yeah, but Einstein he's going to look at the high frequency end, but it'll be the same result. Anyway, so a simple formula will just give you what the entropy is. I'm emphasizing this because I want to emphasize that there's no probability injection into this whatever. This is as close to observation as measuring the energy of radiation is. It's that close. So this is an observational input, or rather an empirical input. And that's why I'm going through this long story. Don't think, oh, there's fancy phase spaces and things. No, there's no phase space in sight. There are no probabilities in sight. It is a measured, observed quantity. Okay. So then Einstein asks, what is the dependence on volume? Well, he says, I'm going to consider a single frequency cut, high frequency radiation, right, of a definite energy, of a fixed energy. And the fixed energy is going to be E. Right? And then he can read off, and it's a simple matter of reading off from the observed properties of radiation, what the entropy difference is when that system with fixed energy lives in two different volumes. Okay, and this is the result that you get. The entropy difference is K multiplied by the energy over h nu times the logarithm of the ratio of the volumes. So where's the h coming from? It's just the Planck's constant that appears in the observational energy formula. Right? So that there's no quantum mechanics as it were being assumed to put in there.
No.
Okay. So now we just apply the Boltzmann principle in reverse, right? And so now it's going to say, okay, there is entropy we know in the end from Boltzmann comes about through a molecular kinetic process. What can we say about the molecular kinetic process? Right? And so he says, okay, well, we'll just take the same guy that we just used a moment ago for the ideal gases and use him in reverse. Right? We know what the S is. Let's move to the W. And now you have the probability is equal to this ratio of volumes raised to the power of something. Right? Now, at this point, you have been set up by Einstein so that it's irresistible to say, oh, that's N. It's N. And we have a system here that consists of N independent points moving freely through this volume. Right? You see, it's just the same guy. It is just completely irresistible to say that. And so, so where is the energy of the radiation? How is it? Well, it's localized into N points. And how many of them are there? Well, it's really E over h nu. So each one of them is going to have energy h nu. Right? And so what have we now found? I think I've quoted the text here. Yeah. And so you now just restate what we've said here. It's I flashed this quote up for you earlier on in order to indicate that there was some hedging going on. But now you'll see Einstein's at this point incredibly cautious. He's saying monochromatic radiation of low density behaves as long as the Wien radiation formula is valid. In other words, we're at the high frequency end of the curve. Right? In a thermodynamic sense, as if it consisted of mutually independent energy quanta of magnitude h nu. He didn't use an h, by the way. He had different constants, but you'll see that in the... Yeah?
Can you remind me of why it is we're restricting ourselves to the high frequency?
The short answer is it works. If you try and do this for the full frequency spectrum, the quanta turn out not to be independent. Since you've triggered a digression, I'll go through the digression. It works very simply in the high frequency end. If you want to ask, how does this behave if I consider the full analysis? This is an analysis that Einstein gives later in 1908 or 1909 that I hadn't planned to talk about, but I'll just mention it briefly because it's worth knowing about. If you do the full analysis on fluctuations, you discover that you end up with formulae that have a sum of two terms in them. One term has a particle type character that looks like this, and the other term has a wave-like character. So if you would ask the Einstein of 1908, you know, the question you asked, he would say, well, yes, I could have made the analysis bigger, but then you would have discovered the wave-like character of light appearing as well. And that is the canonical argument of the era for wave-particle duality.
Yeah, so, and for that very reason, I think that there's an important difference between the hedged thing that Einstein said and your cost on it a moment ago. Because you said, well, hey, it is a system of n-independent points. Well, it acts, for high enough frequency, it acts like a system of n-independent points.
Yeah.
But he also is clear to say in that paper, Wien's formula we know is not valid all the way down.
Right.
And so we're going to have deviations from this kind of behavior for lower frequencies.
That's right. Yeah, but it's very hedged here. But the hedging sort of fades away when you get to other parts of the paper. When he's doing the light quantum stuff, he's not, you know, you don't really get a sense that he's hedged it anymore. He just seems to take it very seriously. Right? I mean, remember what he gets out of the photoelectric. I mean, I don't know what I said here. You know, the photoelectric effect really seems to be telling you that you get, you know, the expanding light system does keep its energy truly localized in those points. Okay, so let me okay, all right. I know I'm hitting you over the head with this, but I just want to say, look, what's he done here? It's the same thing. You know, the result is extraordinary. Utterly extraordinary. But what's the method? The method is exactly what he's been doing before. In the light quantum paper, he's going from the macroscopic thermodynamic properties of heat radiation to the microscopic constitution. Right? That's what you've just seen in inference of that form. That was the doctoral dissertation, from the macroscopic thermodynamics of dilute solutions, right, to go to the size of sugar molecules, Avogadro's number, and it's the same game in the Brownian motion paper. You've got the motion of these little particles that's visible under the microscope, and you're going to the submicroscopic level. Right? And he's using the same essential apparatus, right? Entropy, logarithmic dependence on volume. It's the same guy. He keeps coming back over and over again. Right? And so, yeah. So this is the basic move. When you have an entropy change that goes with a formula that looks like this, right? You can identify that as the number of spatially independent components that comprise the system. All right. When you read through this, it just washes over you, and it's so simple and so straightforward. You say, yeah, that's great. In fact, it's a great deal more complicated than that. Einstein has negotiated a lot of complications here that become completely invisible in the way that I just presented it to you. So I want to look at some of the complications. What's happening here is actually vastly more complicated than this short analysis shows. And so let me just go through some of the problems, and you'll get a sense. There was that moment when I showed you the entropy volume dependence relationship. Remember, you had a log on that? Now, just go slow a moment here. There's something funny about that. What the hell is going on there? Now, you've got to remember that radiation is a homogeneous system, okay? Entropy is an extensive property, extensive magnitude, okay? And so if I have a volume of radiation in a particular frequency cut at a particular temperature, specify all the conditions, and I want to know how much entropy is there, right? I'll get some number. I take a second volume and put it next to it. I just double the volume. It's, you know, I just take the entropy density per unit volume and double it. Right? And so the correct formula for the entropy density of equilibrium heat radiation is you take the entropy density per unit volume in that frequency cut, multiply it by the volume, and you get this guy out. Right? That's non-logarithmic dependence. Okay? All right, so the little flag saying, wait a minute, something's not right here. Now, remember that the logarithmic dependence on volume that we talked about, that goes with the ideal gas law. And the ideal gas law is pressure is blah, 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 but pressure is proportional to 1 over volume. But we know what radiation does. The radiation exerts a pressure. And the pressure exerted by radiation, it's quite fundamental result. You get it out of electrodynamics. It's, you know, just assuming that, even just assuming that you have, well, I won't go to it, but you get it straight out of electrodynamic theory, that the pressure exerted by radiation is equal to the energy density divided by 3. Right? 1/3 the energy density. It's just a standard result. Everyone knows it. It has no volume dependence. So what the hell is going on? All right. Well, let me. It'll take a few steps to get through this. What's going on is pretty subtle. But let's now just remember how things work with the familiar ideal gas law. This is the ideal gas law for an ordinary, you know, ordinary gases. There are going to be n molecules in here, and as the gas expands, right, the pressure drops according to 1 over v. N, of course, stays constant because the number of molecules that are there doesn't change. Right? And that's the trick. N stays constant. Right? What happens with heat radiation when you do the analogous expansion? Put heat radiation inside a box so that it is at thermal equilibrium with the walls, and then slowly expand it. Right? And as you expand it, you create more heat radiation. Right? And so what happens is the pressure, the volume increases. But if we're talking in terms of light quanta, the number of light quanta are increasing as well. So in the course of this expansion process, I think that's what it's the next bit of formula that I've got. Yeah. You have n over v as a constant. So over here, if you're just thinking about this expansion process, you have p is proportional to n over v, n is a constant, so you get the 1 over v that you expect. Over here, p is proportional to n over v again. Indeed, it is the case that the ideal gas law does hold for radiation. You've just got to pull it out a little bit more carefully. But n is increasing with volume, right? Because remember, it's you know, as the energy increases, when you expand it, the number of quanta will increase. Okay, so all right, so that was the subtlety, but you know. So now when you go to apply the canonical entropy formula, you can now see that the formula was being misapplied. Right? In our little thought analysis that we gave earlier on, we were saying, how can it be that the entropy it depends logarithmically on volume when the entropy is just density times volume? It should be it should be linear. But we're not accounting for the fact that as we increase the volume, we are increasing the energy. And that's going to produce a change in this term here, which is going to confound this logarithmic dependence, which is in fact there, right? But it's being confounded by the fact that when you change the volume, the mean energy is going to be changing as well. So that now makes it tough. So how do you expose this? How do you expose this logarithmic dependence, right? You want to go back. You want to pull out, right? So I'll just go back here. You want to suppress this, right? And you want to pull that out, pull that dependence out. So how are you going to do that? Well, you have to find some process for radiation that involves a change of volume, right, but leaves the energy constant, right? And just the normal sorts of expansions and compressions that you do on ideal gases is not going to work, right? Because they're going to be changing the energy, and you get the bad result that I described for you earlier. So what do? Well, there's just one process. Well, just one. There's only one that I can think of, and certainly only one that Einstein shows us. And that's the fluctuation process. If you imagine, right, that the system consists of n points that move independently, right? If they fluctuate over to fill just one side of the chamber, same number of points, you've not done any work, there's been no changes have been made there, it fluctuates over, right? You've kept the energy constant, okay, and you've changed the volume. So in other words, this is in fact a very carefully chosen process, right? Very carefully chosen in order to manifest exactly the dependence that Einstein needed. If you just mechanically think through the volume dependencies, you wouldn't see that. But now, of course, you've got something of an awkwardness here, because the volumes that you're dealing with are not as simple as the volumes that you thought. Everything that we've been doing earlier on had dealt with equilibrium systems. And now it seems to matter essentially that we're dealing with a non-equilibrium system. One of these volumes is the volume that arises in a fluctuation. Right? And now that we had that earlier in the paper, but it wasn't part of the earlier, the earlier discussions. So things are getting, so things are getting complicated. Just repeating here what I said. If you have that process, so you get the constant energy, then that logarithmic dependence certainly appears, and you can get the ideal gas law out again. Okay, but now that's produced more complications. And so what are the more complications? Well, I spent some time going through the apparatus for you, and these were the formulae that I showed you. These formulae were in turn drawn from Einstein's 1903 paper on theory of foundations of thermodynamics, and here's the setup. He's got, these are the Zustandsvariable, we now call them canonical coordinates, but they're the variables of state. And this is the equation of motion, which would correspond to the Hamiltonian equation. I think it's this guy here. And then you get this canonical expression for the entropy. Right? And remember, that was the canonical expression that I fed into the earlier analysis that gave me the logarithm of volume. But this quantity has been deduced only for equilibrium systems, and it's essential that it be, that these only be equilibrium systems, because this is the guy that connects up with the Clausius formula. Right? And you can only make that connection if you are dealing with an equilibrium system for which reversible heat transfers are going to make sense. So it's looking kind of shaky, right? And it gets kind of worse. This is the same fragment of text that I showed you earlier on, and because I wanted to show you this bit of text here. This just says, let P1 to PL be the coordinates of this bigger phase space, right? Well, it's got a fixed number of it's got a fixed dimension, and the one thing that we're pretty sure about with these light quanta is that they don't live in a space of fixed dimension, because you create them and destroy them by expanding and compressing gases. So remember the way the formalism worked. The coordinates with the fixed number of coordinates were identifying a fixed number of points. So that the analysis is of a fixed number of components of equilibrium systems is built in right from the beginning. Right? So there's, you see, complications. There's this enormous gap opening up. between what Einstein actually had in the earlier papers and what he's got now. Right? Right, and so yeah, and of course, you know, he's got other stuff. He's got equations of motion and phase space and so on. He really doesn't have any of that apparatus anymore. But he knows he's right. He knows he's got the right result. You know, and so you know, he's going to remember he's assigning entropy to momentary fluctuation states that are very far from equilibrium. Right? So what do you do? What do you do? Well, this is why Einstein's introduction of Boltzmann's principle, I sort of glossed over it. It was actually a big moment, because he was actually, at this moment, undertaking his own version of that expansion that Jos talked about earlier on. So he actually, so included in this paper is a demonstration of Boltzmann's principle. The demonstration is, once again, one of these incredibly simple things, but it's absolutely essential, because without it, the logic of the paper falls apart, because he doesn't have any justification for using entropy the way that he did. So remember the formula, entropy goes with the logarithm of probability. So how is he going to establish that formula? Well, he's going to say, and this is a much repeated, very, very famous argument now, although I think, and once again, it's another thing that comes up in this 1905 right quantum paper. He says, let's imagine that we have two independent systems, right? System 1 and system 2. Right? Because they're independent, we know that the probability of both of them is just going to be the product of the two. Okay? Now, let's assume that it's possible to write down an entropy function that is a function of the probability only. It was in Boltzmann, right? You know, you showed us the people we're doing this. Let's assume that you can write down the entropy as a function of the probability only. Now, what do we know about entropy? Well, we know that if you have two independent systems, their entropies must add. Right? It's an extensive magnitude, so you just add the two entropies. So what function phi is going to take products to sums? And of course the answer is that. Right, so you can see Einstein absolutely needs that. You know, it wasn't an extra flourish. He really needed to introduce this piece. Otherwise, he's referring back to formulae that he's derived that only work for equilibrium systems. Okay, so I'm now winding down. So I just want to leave you with some thoughts about this. It is sort of classic Einstein. It's really fast. Bang, 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 and he's probably right. But boy, he leaves you with a headache if you think about it, right? You've got to now fill in all of this stuff. I mean, it's beautifully simple. Two independent systems, just multiply the probabilities. We know that entropies add, so it's got to be a log. Well, who's going to argue with that, right? But think about all the stuff he hasn't said. So we have the probability, but what's the probability space, right? We don't really know. We know what it isn't. It isn't the canonical space of his earlier paper. So there are probabilities here. We don't really know whether it's probably going to be okay, but we don't know. Entropy is a function of probability. Well, worked for Boltzmann. I mean, if you think about it, it's kind of, maybe when you go to radiation in other systems, maybe it works for gases, but you go to radiation in other systems. Maybe there are other dependencies that are somehow masked that we need to worry about. That would make a mess of things. The entropy is defined so far for equilibrium states. Is it a definition? All right. Well, yes, it is a definition. That's my view of it. I think it's pretty clear. But wait a minute. If it's a definition, how the hell is he getting the connection to the equilibrium states? Because remember, you were connecting together two volumes of radiation and assigning entropies to them on the basis of an empirically derived formula. right, which only works for equilibrium states. So that the radiation system fluctuates to a smaller volume. Einstein assigned an entropy to that smaller volume on the strength of an empirical formula that holds for equilibrium systems only. So how's he doing that? I mean, all of this is left floating around. I think it all works out in the end, but you've got to really think hard. Now, the way I think that last one works is you have to say the following thing. There's a consistency constraint on a second constraint on assigning entropies to non-equilibrium states, and that is this: if you can somehow freeze that state into an equilibrium state, right, then the entropy you assign to it has to match with the equilibrium entity. Now I used a metaphor freezer. Of course, I don't mean freezer, but somehow lock it in as an equilibrium state. Well, how can that happen? Well, what you do is you suddenly make all the other states, in this case, inaccessible. So the thing fluctuates, and you just grab it quickly. Stick a partition in and just grab it quickly. Right? Throwing in that partition ought not to change the entropy, and then it ought to agree with the equilibrium thermodynamic entropy. And I mean, that's the only way I can see to complete the argument. Right? Otherwise, you can't make that connection from the empirical formula to the Clausius formula, which is in turn the one that's used in order to get the entropy of the radiation. Okay, so that's the conclusion. Just to remind you of where I've been, I wanted to point out for you, and did, that the result that Einstein produces in this light quantum paper really was quite unanticipated and really quite extraordinary. But you don't need to resort to tales of magic to understand how he got it. Right? It makes sense. It fits in with a project in statistical physics that had been underway for quite a few years, and and you can see that the way that he worked developed techniques that he had been honing for other cases that interested him greatly. And in particular, I just mentioned here, he just used fluctuations in that argument. The argument, the Miraculous argument, he used it very fast, it went through very, very quickly, and he did not put a foot wrong. Right? That's what I'm calling this kind of visceral mastery of fluctuations. And I'm rather afraid that, unlike everybody else, I'm finishing a little earlier. Does that mean I don't get dessert tonight or something?
No, that's great. You ended that along me. And I'm sure there's going to be some discussions.
How could there be? It was so clear.
It was clear. Okay. Bill first, because I have a question about the last thing you said.
I
61,
back
page 61.
to the entropy, the last.
You're going to have to adjudicate who. Okay.
Bill first.
Okay. Could you go to the one where you have the Clausius? Yeah, right there.
That's right.
Entropy. Okay. Entropy assigned is the entropy the state would have if it were an equilibrium state.
Yes.
So I haven't yet seen why it's so problematic to just, as you said, take that thing, think of it, leave everything else, think about that. We're going to call that the entropy bit, and then do it that way. I mean, it doesn't seem quite, okay, I shouldn't say so. So it doesn't seem quite as problematic as you're making it sound if you just read the Clausius notion there.
Okay, before you answer, I'm going to ask my question because I was about to say that seems more problematic than you make it sound.
Okay.
And here's
Can I ask you two to just chat amongst yourselves, and when you equilibrate, I'll agree.
And here's, I mean, it sounds good. When I first read the paper, I thought, but here's my worry about this. In the case of the of say a gas, you might fluctuate the subvolume. I might happen to slam a partition in there, and I've caught that, and that's an equilibrium state, and I can convince myself that this is okay because I could connect those states by a QSR process and calculate the entropy.
But you can't, that's the problem.
But in this case, you can't because of that darn N over V is constant.
Yeah.
And if I understand you correctly, what's going to happen is, you send that partition down, and now I've got these quanta in a same temperature but smaller volumes. So the equilibrium state is going to be n over v, a function of only of t. So what's going to happen is those extra quanta are going to get absorbed by the wall of the equilibrium state is actually going to be
Just
that
hold
right?
it, no.
That not right?
Yeah, the system, I think it's not communicating with an external system, because otherwise the temperature's gone up and it's going to lose the heat. So I think you have to assume that there's no energy interchange at that point.
So so we start out with a system of radiation in equilibrium with walls, and then we replace those walls by perfectly reflecting walls, or they don't.
I think that's how you got to do it. I can't tell you that I know how to get all these steps to work out. But
Yeah. So
that's the way that
so the walls aren't black anymore. They're perfectly white.
silver, say.
Or silver. Yes. Yeah, they're going to reflect, but they're not going to absorb or emit.
Yes. So
Okay.
the radiation will stay in there.
Then you could have that smaller number of things. Then you could have that same number of quanta in equilibrium in a. But the moment you try to put it in the equilibrium with black bodies, then
Yeah, you'll be in trouble because the fluctuation, it's fluctuated to a higher temperature.
okay.
I think it's higher. It's certainly a different temperature.
Okay, now I'm worried that I can ascribe a temperature to the system if I can't put that system in equilibrium with something.
Well, let's not worry about assigning a temperature to it. We're doing, it's like it's a Boltzmann style story now, where you just have the total system.
See, it is this little thing.
So you happy now? No. Do you want me to go through the argument for why we should worry about it?
No, I'm slightly happier.
You're happier that you should be worried? Is that it? Yeah, Carol.
Can you go back to the next, going forward slide?
Forward?
Or
I think it's,
the
yeah,
next one.
absolutely.
So I just wanted to ask you to say more about why you think the method of Einstein's discovery was familiar and secure, given all the stuff that you said in the last 10 minutes.
Yeah.
I have kind of talked myself out of that one, haven't I? Yeah, no. Yeah, it got less secure. I think that's exactly right.
It seems more like he pulls it off because he's a genius and he happens to have good intuitions, and he makes, you can reconstruct with hindsight the arguments to be tight.
Yeah, I hate to use the line that Einstein got lucky, because he got lucky far too often. And so my tendency is to assume that that he's telling us less than he knows. The difficulty is to try and pull out the bit that he hasn't told us that he knows. That's what I've been trying to do here. So I mean, clearly the idea that he has is that as long as he's dealing with finite systems, systems of finite, meaning fixed number components, then very clearly it is secure. He needs some sort of generalization of that now. I mean, maybe it's, I don't know. Maybe it's sufficient to say that the conjecture that the fixed number component analysis is more secure if it just applies to systems that are fluctuating that don't have any interactions with other systems. Might he be imagining that a system of light quanta that's not interacting with other particles maybe has a phase space behind it, and, that satisfies all of those conditions? Yeah, at the moment you interact with walls and things, then you need a different physics. Right? I mean, that's the trick. He does go on to calculate the mean energy of each quanta in the Wien regime, and it comes out as, I think it's 3 kT, which would be the equipartition result if you had 6 degrees of freedom. But I don't. I've struggled to try and figure out if he saw any special significance in that. And I think that the only really safe thing you can say about it is that he's just pointing out how in ordinary classical physics, you have this wonderful result where the mean energy of a system with n degrees of freedom is n over 2 kT, and it's so completely independent of all the other properties of the system that it's startling, right? And I think he's displaying a similar sort of independence. Right? You just get 3 kT for each quantity. So I think that's all. Because he doesn't tell you why he calculates that. He just calculates it and says, here it is.
So I would like to know the complications you talked about. So you said Einstein went through the argument very fast and very quickly. It seems very secure. To what extent was he aware of those complications, and to what extent did he deal with those, try to solve them?
I don't know that he ever did. I mean, he got a result that that withstands scrutiny, right? Nothing goes wrong with it, and he can develop exactly those methods. I mentioned earlier on when he comes for his argument for wave-particle duality, it's an extension of these ideas, and he uses very similar methods. He looks at the fluctuations in I think it's radiation pressure, and just by applying analogous techniques ends up with a sum of two guys. I don't recall that anywhere that he now says, okay, light quanta clearly need a new, need a different sort of statistical physics. I don't recall anywhere where he says that. He never goes outside of a Gibbs framework when he does his statistical physics.
Not until the post-Einstein. That's when he says new statistics.
I mean, you've got to remember that Einstein never felt that he solved the problem of quanta. There's the lament later in life that he spent more time on this one question, what are quanta, than anything else. Yeah, he tried various models, but he worked on this stuff. If I remember the way the story goes, he kept working and developing these ideas up until about 1911, when he just decided it was too hard. He couldn't get any further, and that's when he moved back to work on general relativity. And then he got, of course, tied up in general relativity, and that absorbed his life up until, end of 1915.
I think Lon was next.
Do you want to prompt this?
Yeah, I can answer.
If it was something related to this, maybe I'll go first. Mine is kind of a selfish question, so I can't.
Go ahead.
Well, it's a selfish question in the sense that it's related to kind of the things that I'm interested in. And so the way you set this up, you said if you look at Einstein's work against the background of electrodynamics, it's extremely revolutionary. If you look at it against the background of his earlier work, it's you could see the method already. And so you kind of mentioned Planck, and I was just wondering if you'd be able to say more about what you see as the relation between Planck's work and what Einstein is doing here. You said he really identified the problems for the first time. And so I was just wondering about that relation, how that plays into the story.
Yeah, okay. Well, so Planck writes these papers in 1900, and essential to the calculation is that you discretize some energy space, right? And there are different ways of doing it. He has one particular way of doing it. We now recognize that the discreteness that was introduced there was not just essential to getting the result, but it betokened something radically wrong in classical physics. Planck clearly understood that the discretization that he did was essential to getting the result. But there's no indication in the paper itself, in that work, that he realized that it had just revealed some tremendous failure of classical physics. Now, again, my recollections of this are a bit foggy. When Einstein does this work in 1905, I believe he knew of Planck's work, but what he said was, again, I keep looking at Jost because he's written history on this as well, but he said he didn't realize the connection to what he was doing here. That was my understanding. So he thought this was I'll go back. I'll say two things about it because slide where it goes. Yeah, it's a very short analysis that he gives here, but it's the textbook standard analysis. It was the sort of thing that Raleigh and Jeans were doing, except they didn't see it as a problem, right? So this is you know the way it looks. You take a classical radiation field. It consists of a whole bunch of radiation oscillators, right? And the problem is there are infinitely many of them. The Hamiltonian for them is quadratic in the degrees of freedom. You apply the equipartition theorem. You have to assign a half kT of energy to each degree of freedom. There are infinitely many of them, right? And so you've got what Ehrenfest in 1911 calls the ultraviolet catastrophe. So the way that certainly I don't recall any sense of crisis with Jeans. You get the wrong result, so it's a nuisance. But Jeans addressed the problem. The way he saw it was that there is this equilibrium state in which the ether sucks up an infinity of energy. But the fact that we don't see it happening is entirely compatible with the idea that we are just moving very, very slowly towards equilibrium. Right? So the lower frequencies of the radiation field very quickly pick up energy. The other frequencies of radiation are very slow, but in the fullness of time, eventually we're all going to die, right? That was the way that Jeans thought about it in 1905. He corrected Raleigh's early formula. There's no sense of that with Einstein at all. That there's a way out, right? And he's flat. He does exactly the same calculation. Not exactly, close enough, but in concept it's the same. He applies equipartition to classical radiation. There's an infinite energy there. That's not possible. And of course, Jeans has to explain, in the face of that infinity, why it is that we don't have catastrophes. Right? So he comes up with a story. Einstein has got a new story in his back pocket. So he's set up and ready to go. The classical radiation theory is wrong. Is Einstein's answer, and it's going to look different according to this. So when he's doing this, on my best recollection, he doesn't realize that what Planck has done is in the same lines as his. In 1906, there's the paper on specific heats. You know the paper on specific heats, where the classic result is that specific heats remain constant for crystals as you get down to very cold, go down to absolute zero. If you factor in quantum effects, then the specific heat goes to zero. This was a measured, the deviation had been measured, so it was an open problem, and Einstein solved it. I think it was in that paper, or one of the papers written around that time. He then now says in print that he now realizes that Planck was on the same sort of thing as he was. Planck, of course, was very unhappy with the idea of, you know all this. And then, of course, the rest of the story is that Einstein's proposal of the light quantum was not welcomed as a great and wonderful thing that now shows us the way ahead. It was regarded as an awkward oddity, and by very prominent people. So Bohr, in particular, was an opponent of the light quantum. Didn't like it. Didn't want it. There's a famous quote when Einstein in 1914 got one of the most prestigious positions in Germany. He was appointed to what was then the Kaiser Wilhelm Institute in Berlin, now Max Planck Institute. And so the letters of reference that we have, and one of the letters of reference, praises Einstein, but then apologizes for his work on the light quantum, saying something like, even the finest of minds must be allowed their aberrations, right? So the opposition to the idea of the light quantum persisted all the way through into the early 1920s. And so if I remember correctly, the BKS proposal was in part still designed, BKS, Paul Kramer Slater, was still in part designed to get around the, having a light quantum. So Bohr by this point has course, become very very prominent in the field, and he just doesn't like the light quantum. The standard story is that it's the Compton effect that finally seals the deal, and people realize they've got to take the light quantum seriously. So it was a long and solid thing. Of course, at that moment, Einstein could then have been reconciled with quantum mechanics, but of course, at that moment, he decides he doesn't like it. So he was, outside of the historical community, people always think of Einstein as a core figure, but when it comes to quantum mechanics, he was always on the outside. No one liked the light quantum. It was not a favoured hypothesis, and then after the advent of modern quantum mechanics, wave mechanics, matrix mechanics, he disavowed it.
Yeah, so I was curious about the presence of two what looked like quite distinct sort of ways of thinking in the 1905 papers. Because one of the things people like to stress about the special relativity paper is Einstein's reluctance to talk about microscopic constituents of matter, and in some ways to take a very thermodynamical approach. That seems sort of, I don't know, prima facie in tension with the sort of drilling down to providing statistical mechanical kind of accounts of known thermodynamical effects. So I was just wondering, I mean, so it seems like the statistical mechanical kind of line of reasoning was present in this thinking for quite a long time. Was the more thermodynamical kind of principal theory type approach new in 1905, or does that also have a kind of traceable heritage?
Isn't there a Lawrence paper somewhere where Lawrence lays out the distinction that's earlier than Einstein?
Between the principle and...
Yeah, I remember someone hit upon that and told me about it. I
haven't seen Lawrence, but I've seen a discussion in Frank Carré.
Yeah, that's right.
In his lecture in the St. Louis.
That's right. The principles of mathematical physics. I
yes.
think yeah. Poincaré certainly wrote about that. Now, all right. So.
Einstein's discussion of principal constructive theories is only much later. It's only after 1920.
Yeah, no, there's also an earlier version at the beginning of one of the Allen papers when it comes out. Okay, let me I'm trying to figure out what's a useful answer. So let me say a couple of things. That distinction does work for Einstein in the course of his discovery of special relativity. Okay, this is, are we talking about the distinction between constructive and principal theories, right? Does everyone know the distinction? Right? Einstein says there are two sorts of theories out there. There are constructive principles in which you try and build up a complete picture of the world. Kinetic theory of gases would be an example of that, or electrodynamic theory would be an example of that. And then there are, so you construct the world. Then there are theories of principle, where you simply say, look, I don't know all the details, but I know this principle holds true, and I'm then going to figure out what its consequences are. Thermodynamics being the example that he offers, specifically the first and second laws of thermodynamics being the two laws. Okay, so that distinction plays a role for Einstein in the course of his discovery of the special theory of relativity in the following way. He worked for, I think the number was 7 and more years on the special theory of relativity. I'm quoting him by his own account. He became convinced by means of the magnet and conductor thought experiment that the principle of relativity had to hold in electrodynamics. And he was convinced of that fairly early on. And so the project that he embarked on was to find a formulation of electrodynamics that would satisfy the principle of relativity. So he spent a huge amount of time messing around with modified versions of electrodynamics that would have that property. In work that I've done elsewhere, I spent a lot of time trying to reconstruct what the theory is. And I think the theory that he had was very close to a theory that Ritz had developed later on. You give a retarded potential formulation of electrodynamics, and you get pretty much everything that you want by just fiddling with the retardation time in the formula.
You mean you get Galilean invariance?
Yes. Well, you've got to be careful. You almost get Galilean invariance. You can get Galilean invariance for the propagation. What you do is you just fiddle the retardation time, so that the velocity of the emitter manifests in the time of flight. And so I thought that was just terrific. And okay, you've got Galilean covariance, but when you work through the full theory, you've also got to get all the electromagnetic quantities to transform properly under Galilean transformation, and they don't. What happens is the theory fragments into two parts that have two different transformation behaviors, and you're dead. So anyway, so my conjecture is that that Einstein was working very hard on this, and he was trying to get what we would know as an emission theory of light to work. So he's convinced that the principle of relativity has to pertain and make a conductor, all that sort of stuff. And he's trying to get a Galilean covariant theory of electrodynamics going. The core property it has to have is that it has to be an emission theory of light. That means the velocity of light emitted by an emitter, right, will have the velocity of the emitter added to it. So if I'm moving at v and I send out a light beam, it goes at c plus v. Okay, and he tries everything he possibly can to get that to work, and eventually he just gives up in despair because he just can't do it. Now this is, Einstein is in despair at this moment. He doesn't know where to go. Nothing seems to be working. Okay, and the maddening thing about it is that the Maxwell theory, which is not an emission theory, it's just coming out right over and over and over again. Now, of course, we understand, why that is. Einstein's working with the wrong group. He's using the Galilean group for his boosts. He should be using the Lorentz group. And if he uses the Lorentz group, just uses that with the special theory of relativity, with Maxwell's electrodynamics, everything's going to be just perfectly fine. So, and I think he essentially discovers that, right? But now Einstein's got a problem. Remember all the papers Einstein's publishing in that year of 1905. Are you going to be comfortable publishing a paper, in June, right? When in March you've just published a light quantum paper that says that Maxwell's electrodynamics really doesn't work perfectly, and now you're going to publish a paper in which you say we're going to have to overturn Newton's ideas on absolute space and time in order to conform to Maxwell's electrodynamics. Right? So he had a really serious problem, right? And his solution was this invention of the application of this idea of theories of principle and constructive theory. So he's going to, he realizes that he doesn't need all of Maxwell's electrodynamics to get this to work. All he really needs is to revert back to a few principles and then do the whole thing deductively. So what are the principles? Well, one principle is going to be the principle of relativity. That's the one that he's known earlier on. And, that kind of principle talk, by the way, just reinforcing what Yoss said. Poincaré had written a wonderful, Was this the Baltimore Address that has this in it? He lists a whole bunch of principles. This idea of, and the principle of relativity being one of them. So this idea that you could do that was, okay, never mind, don't worry about it. I'm sorry, I'm putting on the spot all the time. It's just so convenient because you know all this.
It was on St. Louis,
St. Louis, yeah. That's right. Okay. But now you need another principle, right? So what's the principle that you're going to use? Well, what's the one thing that Einstein was sure of at this point? The one thing that he was sure of was that emission theories don't work. And so if you look at the first time in the paper that the light postulate is stated, it's the second postulate, it includes the words independent of the motion or the velocity of the emitter. So the first version of it is, there are two principles. One, principle of relativity. Second says that light is always propagated at the same speed independent of the emitter. And then he goes on from there. Now, I'm pretty sure that Einstein was dead against emission theories of light, because it's the one thing I really tracked down. I'm just going to do a bit of advertising here because it's not well known, and I wish to know better. You know Einstein's chasing of the light beam thought experiment? Yeah. It doesn't make sense, right? And I have watched the literature for years of people trying to explain why this thing makes sense. You remember what he says? He says if you chase after a light beam, right, you will discover a beam of light that is at rest, a spatially undulating field, but one that's at rest. I won't go through the whole thing, but I'll just do the first step. But he says that this is not something we ever see, right? And so people are trying to make sense of that. And so, you know, visceral belief in relativity theory. But what's the problem? In the standard ether theory of the time, it is a theorem that if you move at the speed of light, you will be surrounded by a stationary field. It's just a two-line calculation with a waveform. The only thing that you conclude from that is that we aren't moving at the speed of light. Right? That's all. You don't get anything out of that. But Einstein thought this was really troubling. So I finally figured out what the hell's going on here. What's going on is that Einstein is not rehearsing objections to an ether theory. He's rehearsing objections to the emission theories that he himself played around with. Right? Because if you have an emission theory of light, that now becomes incredibly serious. If you have an emission theory of light, you ought to be able to see stationary light waves. You turn the thing around to get it. Don't chase after a beam of light. Have the reverse case, just describe a different frame of reference, of an emitter receding from you very rapidly, right? And if the emitter is moving away from you at the speed of light, it's going to leave behind in space stationary, a frozen waveform, which we certainly never see. So in other words, if the emission theory is right, you have to make a bet that nowhere, anywhere in space has there ever been something moving really fast that's emitting a light wave, because it would leave behind either a frozen waveform or a waveform that moves very slowly. Right? So anyway, I've been arguing this in various places, that this is the way to make sense of that chasing of the light beam thought experiment. When you realize how to read it, so you know what's going on, it's interesting to go back and look at the many accounts that people give. They fake it. They pretend they understand, and they don't. I was going to make a second point. Yes, I think it's a mistake to think of Einstein as a profound methodological thinker. I think that distinction between principled and constructive theories was put in the spotlight because it was very convenient for him at the time. And he then just later reports the ideas that were convenient for him at the time. I see people try to build elaborate theories on the basis of this idea. I don't think it has long philosophical legs to carry us a great distance. But here I probably get myself into trouble.
Well, on the last point, I mean, he only made that distinction in a newspaper article, not in any...
Well, in an Alma deficit once as well, and also in the early part of a paper in an Alma deficit, one of the early papers in 1907. 1907, 1908, you should be able to find it pretty easily. It's widely known, but if you have trouble, I can get you a reference.
But also, he didn't. I mean, there are limits to that distinction. But I also believe Einstein certainly didn't say that one type of approach is superior to the other. They both have their advantages and their disadvantages.
But he does say we only have understanding when we have a constructive theory.
Yes, but we have security. Now, there's one more thing. There's one other thing I wanted to ask you. You've been stressing the notion of spatially localized components in the signature.
Yes, that's it.
Of course, in Einstein's quote about how the radiation behaves as if it consists of quanta, he doesn't necessarily mention spatially localized.
I have to look it up. I don't remember.
And now I'm certainly admit that if you want to talk about independently moving objects, you see they're mutually independent.
Yeah, no, I think he's got the spatial localization somewhere else. I might be wrong with this, but Because it's essential to the argument. The argument doesn't work if they're not spatially localized.
Well, that's my question. I mean, can you explain that? Because as far as I can see, there's not much that depends on spatial localization.
Well, it's this. It's volume dependence. The probability that depends. It's the volume. It's the relationship between probability and volume that depends on spatial localization. Otherwise, you don't get that.
Well, I admit that it's hard to discuss this as long as we don't have a complete example of a non-spatially localized.
This formula works for all v. So make v as small as you like. So let's say you want to give some spatial extent to the objects that you're dealing with, right? Whatever that is, I'm now going to consider a v that is smaller than it, and it won't work. So you have to go down to points. Now, I should mention here that Einstein's argument is not, I presented it the way that Einstein does. Right? I first set you up by showing you can infer from here to here using his methods. Right? Then I first set it up by showing you assume spatial localization, you end up with this formula and then this formula, and then I run it in the reverse direction. And you remember the way that I put it. I was very careful. I said, now it's irresistible. You can't resist identifying that as an n. That's how Einstein puts it. But that's a little bit of an inductive leap, right? Someone who's bloody-minded, right, is going to say, yeah, but maybe not. Give me the missing steps. And Einstein did not. Right? He felt it was strong enough. But the guy who did give the missing steps is John Dorling. And it is possible. Right? It is possible to complete the argument so that spatial localization falls right out of it. It's fiddly. You've got to go through a whole bunch of cases. But I started to do one of the moves that he does. The key move is the following. Take the case of n equals 1. I'm going to take n. So then the probability of localization to a subvolume v in v sub 0 is given by that formula. And then what you do is you make v 1 over n. So you divide the. Maybe I can do it in the air. You divide. No, I'll do it over here. Because, when I draw in the air, I can see it perfectly well, but of course I realize you guys can't. Right, so we're going to divide the volume up into n subvolumes, and we're going to have the case of E over h nu is equal to 1, right? And we're going to ask what is the probability that the entity is in this first subvolume, right? And that's going to be just 1 over n, right? And the probability that it's in the second volume is 1 over n, and the probability in the final one is 1 over n, right? And so these are mutually exclusive possibilities, and they're exhaustive, because if you add them all up, I think I'm getting the argument right. I do. You get 1. So we know assuredly that the guy's in one of these cells, and only one, right? Well, this addition thing isn't going to work because you won't be at exclusivity. But now you can make n as small as you like. Right?
As big as you like.
You get tired after a while. Big. Yeah, you can make n as big as you like. And so you can squeeze these cells down to an arbitrary small size, and that's where you get that's where Dorling argues you get the localization. It's kind of cute, but that just does one case. You've also got to treat all the other cases, and he's got this long inductive, ascent where you go through the various cases.
The other thing I just wanted to ask is it's of course this radical new aspect of these points or quanta that they are not conserved, that they can be created and chosen. When actually did that first appear explicitly in the picture. Was Einstein aware of that? Or did that only write later?
I don't know that there's. I don't know. You mean? I mean the creation and absorption of quanta is it's in the paper. It's a photoelectric effect, all those experimental effects at the end. So he's clearly happy with them, you know, being absorbed and created. But I don't know that he explicitly considers radiation in a chamber being expanded, right? But it's such a an immediate consequence of the whole analysis that I don't know how you could avoid it.
No, neither can I. But I mean, when you ask things like what kind of phase space will we use to describe it with, well, we're going to have to use a phase space with varying dimensions. That's a very odd thing to.
Yeah, I played around for a while looking at Gibbs's grand canonical ensemble because I wondered if something something there. But I don't recall that there was anything anywhere in Einstein where that on. You know, he didn't have that bit of Gibbs.
No.
So there's something here going wrong as regards to themselves when being factors. Well, after all, we know that real photons aren't such that you can visualize not. Just wondering if something right.
Yeah, that's a good question. I don't know. I'm guessing that the relevant approximation is that we're at the high frequency end, and you probably have to keep going to higher and higher frequencies to avoid your.
Yeah, and that I guess with small boxes set their frequency limits.
I mean, that's more reason to take the qualification very seriously. All you know empirically is that this is at least approximately true for radiation of low density and high frequency, and that's compatible with things breaking down if you try to localize it too sharply.
And if that's just worth having as a quick help warning, kind of think with people who, depending on your background, remember this isn't the right theory of photons. This is a kind of classic step all the way towards it. It's not actually the right theory.
It's a heuristic point of view.
It's a great thing.
Yeah, what's that? Is there a title on a heuristic? Excuse me, on a heuristic hypothesis concerning the creation and conversion of light. Wasn't that the title? Yeah.
It's the wrong hypothesis, but the idea of getting the right one is a hypothetical feels it's a nice step all the way.
Okay. No more questions. Let's thank John.